This is Chemical Processes for Micro and Nano Fabrication. I'm Chris Mack, and this is Lecture 8, Transistors. We're going to talk about a number of different kinds of transistors, but because this class is focused on CMOS technology, we will spend more time on MOS transistors and CMOS transistors. Our reading is Chapter 16 of our textbook by Campbell. Bipolar transistors were the dominant technology through the 60s and early 70s and still important today for some applications. Two kinds of bipolar transistors called NPN and PNP. Different flavors, but they basically behave in essentially the same way. These bipolar transistors are three-terminal devices, and they have really two applications. You can use them as an amplifier, where the current into the base is amplified, or you can use it as a switch, turning the switch on and off, and it's a current controlled switch. When you add current to the base, it switches on. Take away the current from the base, it switches off. Supplying the current to the base is kind of the input signal, and then the current that flows from the collector to the emitter is the output signal. We can switch the emitter current on using the base current, so it acts as a switch, or the emitter current, the current coming out of the emitter going from the collector, is essentially an amplified version of the base current. This allows us to use bipolar transistors as amplifiers. And in the early days of logic, we often used bipolar transistors to make our logic circuits. ECL, emitter-coupled logic, was common. It's not very common today because of being replaced by CMOS. We'll talk about that later. Today, bipolar is most commonly used in high-frequency circuits, radio, wireless kinds of circuits as amplifiers. And if we combine with CMOS, which we commonly do in some applications, we can put both bipolar and CMOS technology on the same chip, and then we call it BiCMOS. Cell phones are full of chips with BiCMOS technology. One of the applications for these amplifiers is to amplify a signal being picked up by an antenna. An antenna picks up an electromagnetic wave. The voltage signals are extremely tiny, very, very small amplitude signals. We need to amplify them in order to process them in some way, either in an analog processing fashion or in a digital processing fashion. We still need to amplify these tiny signals being picked up by an antenna, and so bipolar transistors are often the technology we use to amplify those signals. MOSFET, on the other hand, is a very different kind of operation. We see the symbols up at the top. In fact, there's a couple of different styles of symbols. Little circle here, or the arrow pointing in, is the P channel, and no circle, or the arrow pointing out of the source, is the N channel. And MOSFETs are, first of all, FETs. They're field effect transistors. What that means is we use a voltage to control the operation of the device, a field, an electric field, versus the current, like in the bipolar device. These field effect transistors can act as amplifiers, analog amplifiers, or as digital circuitry for logic. It's a voltage controlled switch, though. And instead of the base, it's the gate that controls or switches the current going from the source to the drain, or drain to the source. The voltage on the gate is the control, as I said, and MOS is the most common, most popular type of field effect transistor. MOS stands for metal oxide semiconductor. It's also called a metal insulator semiconductor field effect transistor, or MOSFET. But even when we use an insulator that is really can't be described as an oxide, we'll still often use the acronym MOS for these devices, just for historical reasons. But we'll see what we mean by metal oxide semiconductor for these devices in a moment. let's begin not with how we make one, but with just a portion of a MOSFET device. We're going to show you the source and the drain implemented in a substrate. I'll pick a particular flavor. We have a P substrate. That means the substrate has been doped P-type with acceptors. And we've got N-type source and drain regions that have been diffused into the substrate. So what do we have? Well, the N here and the P makes a PN junction. Right? Here, here. And likewise, this N and the P region makes an NP PN junction as well. What might happen if we apply a voltage from the source to the drain? Well, either way you apply it, a positive voltage on the source or a positive voltage on the drain, notice that one of these PN junctions will always be reverse biased. If I forward bias the source to the substrate PN junction, that means I will, by default, reverse bias the drain to the substrate PN junction. I can never have both of them forward biased at the same time. In other words, we can think of each of these PN junctions as a diode, but the two diodes in series are pointing away from each other. Remember, a diode is like a switch that only allows current to flow in one direction. So in this configuration, I could never get current to flow from the source to the drain, because no matter what, one of these diodes will be like an open switch while the other one is closed, and I'll never be able to get current to flow. So how can we change this situation? Well, that's where the gate will come in. So here's my source and my drain, but now let's add the gate. And again, I'm not really describing the manner in which these are made, just showing you the components, but we're going to put on top of this region between the source and the drain a thin oxide layer, a thin insulating layer, and then on top of that we'll put a metal. So this gives us the metal oxide semiconductor stack, where our MOS gets its name, metal oxide semiconductor. And electrical connection to that metal will turn that piece into the gate. And it will be the gate that we're going to use to change the behavior of the connection from the source to the drain. All right. When we don't apply any voltage, remember that the source and the drain cannot allow current to flow between them because one of these PN junctions is reverse biased. It's an open switch. But what if we put a positive voltage on the gate? Positive voltage, there'll be a whole bunch of positive charges hanging down in the metal, here down at the bottom. I show them, but basically the whole metal will be positively charged. I've got an oxide insulator, so I can't get any current to flow directly from the gate to the substrate. But this positive charge will have an influence. Right below the gate oxide is the P substrate. That is a material with lots and lots of mobile holes, mobile positive charges. Now, when the mobile positive charges down here in the substrate sees or is influenced by the electric field caused by the positive charges here, well, the like charges will repel. The positive charges here will move away. So we can see that those positive charges will get pushed away, and any negative charges present will be attracted up to the top. Well, this is a P substrate. There aren't many negative charges, but there are some. There are a few free electrons. And remember that in a material without an applied voltage, we've got constant generation and recombination going on. So generation means we spontaneously get an electron and a whole pair being generated, and then they find each other just as fast and they recombine. And so we have an equilibrium in the generation and the elimination of holes and electrons. But here now, if we have generation and we form an electron in a hole, the gate voltage is going to push the hole away, attract the electron, so that we won't get recombination. Instead, we'll get an accumulation of these mobile electrons in a region just below the gate oxide. Now, if we apply enough voltage, we can get enough electrons, mobile electrons, to be present in this region just underneath the gate oxide, that we can have what's called an inversion layer. And by inversion layer, what we mean is we have achieved the opposite majority carrier. So in the P substrate, the majority carrier is holes. We have a lot more holes than electrons. But in this thin layer just below the gate oxide, we will get a majority of electrons. In other words, the layer will invert and become N-type. That layer can extend all the way from the source to the drain because of the configuration here, kind of cut off. The gate ends right when the source begins. So we get a channel of N-type material connecting the N-type source to the N-type drain. So we call this an N-channel device. And guess what? With that N-channel, I can now conduct electricity from the source to the drain. I have closed the switch. If I apply a source drain voltage, say a positive voltage on the drain, it will drive current to the source, and we've got a closed switch. But only when I have a positive voltage applied to the gate. I showed you the operation here of an N-channel device. Of course, if I switched all of the N's and P's, if I had an N-type substrate and my source and the drain were both doped P-type, and I used a negative voltage on the gate, I could get an inversion layer that is a P-channel. So the same kind of operation would work where if I flipped everything N and P. So we have two types of MOSFETs then. The N-channel, which I just described how they behave, but also a P-channel, which works in a very analogous way. The voltage required to get an N-channel to form, this inversion layer to form, turning on the device, the minimum voltage required to do that is called the threshold voltage. And it's one of the most important parameters of a MOSFET. If we exceed the threshold voltage, we turn on the device. If we go lower than the threshold voltage, we turn off the device. For an N-channel, or sometimes called NMOS transistor, V threshold is positive. For a P-channel MOSFET or a PMOS transistor, we have a negative threshold voltage. This threshold voltage is a function of the properties of the material, what kind of material makes up the oxide, what kind of material makes up the metal, but it's also a function of the oxide thickness and the doping in the channel region. So in fact, we can adjust the threshold voltage by changing the oxide thickness, which is something that's easy to do in our processing, or by changing the doping in the channel region, in the region just below the oxide thickness. And so this doping of the channel region turns out to be very important to adjust to get exactly the threshold voltage we want for our circuits. Alright, so now we know how to make, at least we know how they operate, an NMOS transistor and a PMOS transistor. What we're going to do now is connect the NMOS and the PMOS together in a very specific way that we'll call CMOS. What is CMOS? CMOS is complementary MOS transistors. Complementary because I have one PMOS transistor and one NMOS transistor connected together in certain ways. In particular, we're going to connect the gates of the CMOS to the NMOS so that one gate structure will control both PMOS and NMOS transistor. Here's maybe the simplest configuration we can do. So remember my symbols up here. This circle tells me that this is a P-channel device. So I've got a P-channel device right here. And then here I've got an N-channel device. This is the gate, and they're connected together. I'll label the input A. So I'm going to think of this as an input signal coming into the gate. All right. VDD, this will be a positive voltage that's connected up here. VSS will be a negative voltage or low voltage. And notice that I have the source and the drain connected. So if this is the source and this is the drain, they are connected, the NMOS to the PMOS right here. So how will this circuit operate? Suppose I put a positive voltage in at A. Now remember, for a positive voltage, we turn on the N-channel device. So this is turned on. That means I've closed the switch between the source and the drain. I've created a conducting channel. It's like a wire going from source to drain. This means that current can flow, but it also means that the voltage of the source will be about the same as the voltage of the drain. It's like connecting them with a wire. In other words, Q will take on the voltage VSS when I put a positive voltage for A. Now that's the N-channel device. Think about the P-channel device. If I have a positive voltage on a P-channel device, this thing is not turned on. It's an open switch. No current can flow. And so the voltage at Q is independent of what happens with this device because it's just an open switch. It's like it's not even there. Now, let's do the opposite. Let's put a negative voltage for A. We'll set A to be equal to VSS. That turns off the N-channel transistor. This becomes an open switch, open circuit right here. But it turns on my PMOS device. This creates a P channel and short circuits the source to the drain. In other words, Q will have the voltage of VDD. Let's think about what we just did. Positive voltage at A produces a negative voltage at Q. Negative voltage at A produces a positive voltage at Q. We call this an inverter. If we label the positive voltage to be a 1 and the negative voltage to be a 0, then whenever I put a 1 in A, I get a 0 at Q. Whenever I put a 0 at A, I get a 1 at Q. I've just made an inverter circuit. And inverter circuits are, of course, very useful in and of themselves, but I can build more complex logical circuitry using inverters. Also, very important to note that at any setting of A, whether it's a high voltage or a low voltage, one or the other of the two transistors is turned off. So no matter how I set A, one of the PMOS or NMOS transistors will be an open circuit. So no current is flowing from VDD to VSS. I get essentially no current flowing in this circuit at all when it's just sitting there at either state. It only draws current when I switch A. Switch it between high and low voltages, I will get some current flow then. Otherwise, I won't. That makes CMOS a very, very low power, and that's quite significant. And this is why CMOS has become so popular as we've added first thousands and then millions and now billions of transistors in our circuits. Finally, I'll show you one last CMOS circuit. This is a NAND gate. A NAND gate gives me a certain logical operation. AND means I will get high output if both A and B are high. If A and B are both 1s, I'll get a 1. Otherwise, not. And then a NAND is a not AND, so it simply adds an inverter at the output of the AND operation. And this is how a NAND gate would be configured with it's still CMOS. Note that the gate A is connected to both the PMOS and an NMOS transistor. The gate B is connected here and here. So I've got a PMOS and connected together. So it is CMOS complementary. And then this is a top-down view of the physical wiring of the things together. The blue is the metal that makes my VSS and VDD. I've got green as the gate polysilicon material that forms my gates. And you can see the gate of this transistor and this transistor are connected. The yellow is the P diffusion that makes up my PMOS transistor, and here's the N diffusion that makes up my NMOS transistor. Contacts allow me to make contacts to electrical contacts to the various components. Now, we'll see a lot more about about this and how it works as we go through the class and talk about all the individual unit process steps. But this gives you a little bit of a feeling for how we're eventually going to configure all of these different materials to make an actual device. All right, let's review what we've learned in this section. In Lecture 8, you should be able to answer all these questions quite readily. When and why are bipolar transistors used in circuits? Describe the basic operation of an NMOS and a PMOS transistor. So if I gave you either one, you should be able to tell me exactly how that works. What is an inversion layer? Define for me the threshold voltage in the context of an MOS transistor. And finally, what is the advantage of CMOS circuits for logic? Why do we use them? Why are they so popular today? Well, that's my lecture. Next time we'll talk about the basic process steps used in making CMOS transistors, and then we'll begin our unit operations to go through each of the individual process steps week by week. Thank you.